Awesome. I'm Abhishek. I'm the co-founder and CTO at True Foundry, where we basically build a machine learning platform on top of Kubernetes. And today I just want to share a few learnings that we have had along the way. Of if you are planning to do ML on top of Kubernetes, some things that you need to be wary of, some things that probably will make your life easier if you're trying to do machine learning on Kubernetes. So fundamentally, you might think like, why is ML different? At the end of the day, it's software. There's no fundamental difference between software and running an ML service at the. But there are the major differences come from the fact that the problems in ML are probably day hundreds problems in software. A lot of the things that you will probably encounter in a much later phase or might not encounter at all, you start encountering on day one. And that's what makes this problem a bit more complicated than just hosting traditional software on Kubernetes. So I'm just going to go into a bit of the problems that what makes it quite different. So the first thing that you will encounter is different types of hardware, which probably is not a case if you're just hosting software on Kubernetes. Like you have, and it's not just, all of you might have heard of GPUs, but there is this custom hardware by like Inference by AWS, there is TPUs by Google. Even among GPU, there are multiple generations of hardware. Even among CPU, you will find like significant difference in performance between Intel and AMD processors. So like it becomes very important for data scientists and developers to be able to target a certain hardware. And that's what kind of makes it complicated because it's no longer just slap your software onto a certain machine and it starts running. The second thing that you'll encounter is like these huge Docker images, which you don't encounter in software. And the impact of that is basically suddenly you'll find like your startup time is very high. Your auto scaling is not working because it's taking a long time for you to auto scale. So these kind of things, your application is very slow. So these kind of things start happening because of this higher Docker image sizes. And then one more thing will be like your slower iteration cycles. Especially if you're testing things on GPU, you cannot test it on your local laptop. So you have to like now build your image, send it to the GPU machine, wait for it to run. If every Docker image starts taking 10 minutes to build, you'll be really frustrated by the end of it because your iteration cycles are super, super slow. Then comes auto scaling is actually no longer that trivial as you see in software. In software, most of the time, CPU-based auto scaling or sometimes memory-based auto scaling will work. In ML workloads, probably almost never your CPU or memory-based auto scaling will work because the way these machine learning libraries are designed, they're designed to max out your CPU or GPU capacity. Like every time you're processing a request, it will actually hit 100%. So like a good machine learning library is supposed to hit 100%. So if you are auto scaling in terms of like CPU usage, you'll suddenly see like your CPU usage going to 100%, then dropping. So the auto scaling will be all in chaos. So the most beneficial thing that we have found for auto scaling is request count. Like auto scale based on request count, which doesn't come natively with Kubernetes. Like there's no metric of what is the request count. So you have to logging like custom metrics or use like Envoy metrics, or if you're using service mesh or things like that, and then auto scale based on that. Then you also need auto scaling like if you're using Jupyter notebooks or something like IDEs on top of Kubernetes, then you will probably need to auto scale based on time or activity. Like when a data scientist stops using a Jupyter notebook, that's the time you should scale it down. So this metric is more on like if the kernel is being used rather than any other metric of request count or anything like that. So that further makes it more complicated. And then one more problem that you'll see is like auto scaling is very slow. Your GPU machine will take 5 minutes to come up. By the time your spike of requests would have already gone through a failure. So that is one more problem you'll encounter. Model download and caching is another thing that we'll need to sort. So a machine learning service is nothing but basically you have a model file. A service is supposed to load that file into memory and then pass the request through the file and give you an output. That's pretty much what an ML service hosting looks like. There's no like magic to it. But the problem statement becomes like these files are really big. These are no longer, in software, we are used to loading like configuration files that are like some KBs or maybe like some MBs in size. Now we are talking about like models which are gigabytes in size. And like if you are dealing with LLMs and things like that, like Llama 70B is 150 GB in size. So to load that into memory, it will take you a lot of time to load it from disk. How do you get into disk? How do you get it into the container in the first place? You can say that, okay, I'll bake it inside the Docker image. I'll put the model inside the Docker image itself. But then you have a problem because the models are changing really fast. In ML, the differentiation is your model versions change, your code remains relatively static. Whereas in software, like your code is changing more faster than anything else. So in that case, like you're literally rebuilding the Docker image again and again every time your model file is changing. The other option, you can say that, okay, I'll download the model whenever my application starts up. Well, you can do that, but that means like if you're running 100 replicas or 100 pods of the service, you're literally downloading the model 100 times. From maybe your S3 or wherever your blob storage, wherever you're storing the model, you're downloading the model 100 times, which will incur you more cost. First of all, your S3 read costs. The second thing, your applications will start up slow because you're doing the same download 100 times. So how do you solve this model being present on the disk inside the container problem? Then cost is also something that you'll start worrying about on day one. Because running one GPU is, even one machine, like if you run one CPU machine, you'll probably not bother about cost at all. But running one GPU machine, if you take into account like running 800 GPUs, it's $3,000 a month. So it's no longer like cost is an afterthought. You can worry about it a bit later. So you have to think about cost, and that's what motivates you now to think about if I can use spot instances. How do I optimize resources? Have I written the code in an optimal way? So these are other problems that you'll start encountering. Then to save cost, this is basically an artifact of saving cost. Like as I mentioned, one GPU will cost you $3,000 a month, but maybe your whole application, one application doesn't need the whole GPU. So then a requirement will come up to you that, okay, I want to use can I put like 4 workloads on the same GPU that allow them to share the GPU. Now in CPUs, we can always request for 0.3 CPU, 0.1 CPU. You are allowed to request for fractional CPUs. In GPU, that thing doesn't exist. If you cannot ask Kubernetes and give me like 0.3 GPU. So then you have to like implement something custom to allow this fractional GPU support on Kubernetes. And this thing, like, by the way, like if you're doing just VMs and all, like a single VM, usually developers just go and run 4 workloads on the same VM and let them share the GPU. So that's how they do it. But on Kubernetes, you can't do that anymore. Because the moment you can only ask for 1 GPU at a time, and the moment you ask for one, that 1 GPU will be reserved for that single workload. And then one of the major problems is also the knowledge gap among the data scientists. Like data scientists are very good in doing ML. And it's kind of unfair to ask them to also understand Kubernetes, which is quite complicated. So they kind of prefer an abstraction where they don't need to understand what's going on underneath. And you have to give them a higher level of abstraction. So then basically you have to kind of build those abstraction layers on top. And how do you build those abstractions so that you have enough flexibility while at the same time making it simple? The standard trade-off of building abstractions. So that is another problem that you'll probably encounter. So this is where, these are some of the problems that we saw. And that's where we started building this kind of an ML platform on top of Kubernetes. We wanted to go via Kubernetes and not anything custom because of the huge support system around it. Like it runs on all the 3 clouds, on your on-prem machines, and all of that comes for free with it. So we wanted to use that. And that's where we kind of dived into like what can we change, or what are the kind of abstractions we can build on top of Kubernetes to make running ML really easy. So this is kind of an architecture diagram that you will find. Like this is nothing very special, but basically it kind of, you have your infrastructure providers at the bottom. It can be on-prem, or you can have your AWS, Azure, GCP, or even other clouds. Doesn't matter where you get your machines from. On top of that, you are basically putting this device drivers, like GPU drivers, or you're putting your CSI drivers, storage drivers to talk to your storage, to where to download the models from. And you put this Kubernetes layer on top. On the top of the Kubernetes layer, you need to have these modules for, and some of these modules will be common for even software, so there's not much difference. Like you'll need a CI/CD framework, you'll need a service mesh framework, you'll need access management, you'll need cost management, you will need to manage your secrets, you'll need to manage your workflows or pipelines, so you need a workflow engine. You can choose different softwares available for that, but you'll need to have something that does the job here. And on top of that, you make an ML platform set, which kind of gives those abstractions to data scientists that they're looking for. They're looking for a way to train a model. They're looking for a way to host a model as an API. They're looking for a way to basically track all their ML experiments. They are basically looking a way to deploy an LLM, or to maybe run a Jupyter notebook on the Kubernetes. So that's what they care about. So you kind of build these abstractions on top of this ML platform layer. And on top of these is where the data scientists will build all the applications. Data scientists, ML engineers will start building all these applications, all recommendation engines, forecasting engines. Now there are a lot of ML applications that have come up. So this is what we kind of did, like to satisfy all these yellow boxes that you see, CI/CD, service mesh, and all of these things. We kind of install a certain few components on the cluster to make it ready to build the ML platform on top of it. So what we installed is basically we use Argo CD for all sorts of deployment. Every deployment becomes an Argo CD application. Argo Workflows is used for running pipelines and jobs. This is basically for training a model. For your batch inference job is where you can use Argo Workflows. Auto-scaling, we use Keda. Most of the times, HPA doesn't work properly because in ML workloads, you probably need to auto-scale based on request count or based on the queue length. So those kind of things are available in Keda, so your HPA will not work in most cases. For Jupyter Notebook, we wrote our own notebook controller that kind of manages the Jupyter Notebooks, the lifecycle, automatically shuts them down once you stop using them. This is inspired by the Qflow notebook controller. Then you can install Prometheus for metrics. You can do Victoria metrics or any other thing, it doesn't matter. For logs, you can install any of the solutions, like there's this Loki, Datadog, ELK stack, or anything, it doesn't matter. We also wanted canary and blue-green rollouts or traffic splitting. So this is one more thing that becomes evident in ML from day one. Like your data scientist will probably ask you that, okay, I want to test this new version of the model with 1% of traffic, which usually you'll not get a requirement on day one because models are non-deterministic and nobody can tell you if this model is correct. So they usually want to test it on smaller percentage of traffic and then roll it out slowly. So that's where you need this canary and blue-green on traffic splitting support. So that's where we use Argo rollouts. For model caching, we use volumes. These volumes will be powered by different drivers on different clouds. For example, in AWS, you'll get EBS and EFS. On Google, you'll get file store. And in Azure, you'll get Azure Container CSI drivers. Cluster autoscaling is another thing. Cluster autoscaling will also help you get those different types of hardware. Like a data scientist will tell you, or an ML engineer will just tell you, I need a GPU machine. Now, how do you attach that GPU machine to the cluster? You can either have a cluster autoscaler inside that, or what we use in AWS is Carpenter. That kind of brings up these nodes dynamically if you have worked with Carpenter. Have people worked with Carpenter here by any chance? Nice, yeah. So Carpenter is a thing that makes it really easy to bring nodes dynamically in Kubernetes. It works only on AWS. On GCP, there is something called node auto provisioning. So on GCP, you will probably use node auto provisioning. And on Azure, Azure comes with cluster autoscaler already inside the cluster. But you have to create those node pools beforehand in Azure. Then comes accelerators. So this was the part that I was talking to you about, like AWS, GCP, and Azure. Like there are different operator configurations that you will need. Even the device drivers, it's not the same. We have had to make like some modifications to make it work on all the three clouds. So your GPU operators, your Inferentia operator, even if you're using AWS Inferentia, you also need a custom scheduler in Kubernetes. So installing all of those on Kubernetes layer. For ingress or service mesh, we use Istio. That allows us to do those traffic splitting and things like that. And then for fractional CPUs that I mentioned earlier, there are two techniques of doing fractional GPU. One is time slicing and one is this MEG. Both of them have like certain areas where they work and where they don't work. For example, this MEG will actually provide you GPU isolation. So what that means, if you are saying I need 0.3 GPU, you cannot go beyond 0.3 GPU in the MEG framework. So it is actually providing you GPU isolation, but then the catch is it only works on A100 and H100 GPUs. It doesn't work on all GPUs. If you want something to work on T4 or V100 GPUs, you probably need a time slicing concept. Time slicing just allows you to put workloads on the same GPU. It doesn't really give you GPU isolation. But it can be useful for saving a lot of cost in certain scenarios. Like many times you have like very few requests a day and you just want to share the GPU among multiple workloads to lower the cost. So it can be useful in certain cases. So then the implementation of time slicing is also different for every cloud provider. In AWS, you have to do something different. In GCP, different. In Azure, different. So building that abstraction layer that works on all the three clouds in a generic way is something that we kind of worked on here. So this one is kind of what we do. So we also create a Python DSL because data scientists and ML engineers are most comfortable with Python. If you throw YAML at them, they don't usually like it. They don't like writing YAMLs at all. They'll start hating you if you ask them to write Kubernetes YAMLs. So we kind of do that. We ask them to write Python code. We take this Python code, we convert it to Kubernetes YAMLs according to the cloud provider that you're going. So this is where all the intelligence is kept inside, that if you're deploying on an AWS cluster, if you're deploying on a GCP cluster, the same requirement gets converted to the appropriate Kubernetes YAMLs, and then we go and apply those Kubernetes YAMLs on that specific cluster. So you don't need to learn about anything about Kubernetes, how to write the YAML or anything like that. This system kind of takes care of all the transformations and does it for you. And this is how we kind of support multi-cluster. So you basically, so as I mentioned, like we support deploying on all the 3 clouds. And we kind of give you a DSL that gets converted to the appropriate YAMLs in all these 3 clouds. So then we have this multi-cluster management solution where you can just say that, okay, maybe this GPU is available in Azure. This is my code. This is the model that I want to deploy. Go ahead and deploy it on Azure. Then we take care of everything else, like making sure the Kubernetes cluster is configured properly in Azure, converting your spec into the appropriate Kubernetes YAML spec of Azure that is needed. So Kubernetes is cloud native, but when you start using Kubernetes among the 3 clouds, you'll find that there are subtle differences between them. It's not the same that you throw the same YAMLs at something and it'll just work. Especially when you have these hardware configurations of GPUs and things like that. They differ across the clouds. Even the availability differs. So this is how we kind of build this multi-cluster solution. And one of the cool things about this is you can connect as many clusters as you want to the central control plane. And these clusters can be on-prem or across clouds. And you are just writing, like, you are just giving me the standard spec, and we kind of know how to convert it to each of these clouds. So you can have inside your own company, like, as many clusters as you want. You can spin up like clusters via CI/CD or anything like that, and each of these clusters can be private. So the control plane doesn't connect to these clusters via ingress. It's the cluster that connects to the control plane. So you can even make these clusters private and still be able to operate this entire system. This is one thing I want to walk you over. This is like one flow that seems very simple, but when you start implementing it, suddenly becomes very complicated. So the problem statement is that, okay, I am a data scientist. I have a model. The problem statement that I was telling you before. I have a service that loads this model from disk and then does the inference and gives you back the result. This is the problem statement. Now, how do you do this? Like, as I mentioned before, you cannot bake it inside the Docker image. Not a great idea. You can download it on your app startup. Not a great idea because your startup time will increase. Your auto scaling will be slow. You're downloading again and again. So the solution there is use a volume. Like, you can use a network volume, like something like EFS in AWS, put the model on that volume, and then have these multiple pods mount that model from that volume. Now the question there is, like, when my model version changes, who is going and updating the model version in the volume? So like, if somebody has to like actually log into the volume and update the model version, that is one of the approaches that you can take, which requires manual stuff. The second problem is that you can't just replace the model. For example, you already have something running in production. If you go ahead inside the volume and you just replace the model back then, if any pod restarts in the meanwhile, it will start picking up the new model. So you have half your service running the older model, half your service running the newer model, which is kind of non-deterministic. Like, you are not actually controlling, you have not really rolled out the new model, but some pod got started and it found that new model in that volume. So basically what we did was, as a data scientist, you just give us the model location that, okay, my model is sitting in this S3 location. And then what we do internally is, and you give us the service code. So the service code is reading from the file and then doing the processing. So what we do is, you give us that, we automatically create a volume for you. We run a pre-sync job, like if people have used Argo CD, have people used Argo CD here? Okay, nice. So if you have used Argo CD has something like a pre-sync wave. So basically what you can do is, before doing the actual deployment, you first download the model from your S3 to your volume. So that's the first thing you do. Then you start the rollout of the pods. Now, even when you start the rollout of the pods, we actually give you the location of the model as an environment variable. So we ask the users that don't hard-code the model location from where you are reading from the file. You take this as an environment variable that we will provide to you. So if your version v1 is running, we give you that, okay, your model path is /model/v1. So you read the model from the file, and when your application starts up, we make sure that you find the model at the disk. Because we have already made sure that while deploying, we first created the volume, we downloaded the volume, we downloaded the model to that exact location in the volume. So you don't need to worry about how that model is reaching that file location. That is all taken care of by us. Now, when you want to upgrade, you might need to change the code or you might need to change the model. Those are the two things when you want to upgrade your deployment. If you want to change your code, we will automatically see that your model version has not changed. So we'll not download anything again from S3, and we'll just switch the Docker image URI, which you kind of do on Kubernetes. You'll have a rollout, your new service will start, still read the old model. Then if The second case is when your model version is changing. If your model version is changing, what we do is we see that the model version has changed. We download the new model version to /model/v2. And then we restart the deployment with the model path as /model/v2. So every service that comes up new is getting the new model version. And then we go ahead, after the rollout is complete, we automatically go ahead and delete the model v1. So that is also important because otherwise your volume will keep growing on size as you're rolling out new versions. So this entire lifecycle is fully automated for you. And as a developer, you don't need to worry about how do I store it in the volume, who goes and deletes it, and all of that is taken care of automatically. That's pretty much all from my side. Thank you so much. Any questions? Yeah.
So the ML platform is specific to Kubernetes or other particular distribution like ECS or Rancher?
So primarily, so just to iterate the question for everyone, like, sorry, your name, please?
Saurabh.
Saurabh.
Yes.
Yeah, Saurabh is asking if this ML platform works only with Kubernetes or also our container orchestration platforms like ECS or Rancher. So we work with Kubernetes only, but Rancher is Kubernetes. So any Kubernetes distribution, it will work well. It doesn't need to be the 3 clouds, but it doesn't work with ECS. So yeah. Any other questions? Yeah.
What is the content of the model? Why is so large the file? Like, why cannot be layered?
So models are, it depends like the number of parameters in the model. For example, Llama 70B is 70 billion parameters. 70 billion parameters, each parameter, if you consider it as an int, you're having like 4 bytes for that. So that's how the model, it's the weights of the model basically. The more complicated a model is, the more number of parameters it will have and the bigger the model will be. That's how you're getting GPT-4 is so smart because it is very huge. That's why it is big. Yeah.
How do you take care of the distributed model training as well as deploying of such models which are huge?
Yes.
You need multiple systems to actually just do inference as well as training aspect.
Yes. So the question is like, how do you do distributed node training and inference? Inference is relatively easy because it's like a scaling of a microservice. So you use the same technique, like 170 billion Llama 70 billion model will be around 150 GB in size. The same thing that I discussed last, like you download it to a volume and then you load it up. The difference is like you need to kind of put very fast disks underneath because oftentimes the time to load 150 GB from disk into GPU memory is very huge. So that's why you have this NVMe disks and all that kind of make the loading really faster. So that's what we automatically choose the disk also for you based on the model size. So if your models are huge, we kind of give you a very premium disk. We choose we choose the most premium disk in the cloud provider because we don't provide infrastructure. So we do that automatically. Distributed node training, again, is a bit of a hard problem on Kubernetes because you can do it. There are libraries that automatically coordinate among different nodes. What you need to be careful of is the network connection between the nodes. They need to be NV-linked because oftentimes the time to transfer the data between the nodes becomes so slow that your training will go very slow. So then you build those super clusters and all, and node training, like you don't need to do. The major problem comes in downloading the data. Otherwise, the software has already come for distributed training, and you can just load it up. Operators come on Kubernetes, and that should do their job. The primary problem is how do you load those data parallelly in different places. So you can use S3 streaming and things like that. There are a lot of techniques to do that, but those are the things that you do.
You use like Argo workflows to do those things. Is how compatible or how has your experience with distributed training, but with Argo workflows?
So Argo workflows we don't do distributed training with. For distributed training, you need something different. Yes. So Argo workflows is only for running standard pipelines, like the naive pipelines. For distributed training, you need different softwares. Yes. Cool. Awesome. Thank you, everyone. Any other questions? Cool. Thank you.